Okay, so we, like I said, still catching up from running behind a couple of days ago, a couple or to about 2 lectures ago. So I guess I'm just going to jump right into it. This lecture is going to be most of the lecture H slides that are online, with a couple of lecture G3 slides that were missed last time that are kind of been interspersed into there. So just looking forward, I'm going to skip over some of these announcements because there's not really any new updates, but I do want to mention that in the lab schedule, there's no formal lab this week. The next formal lab is technically assigned next week. So last week was the input analyzer, next week is the output analyzer. This week's lab is really just meant to be free time for you to be able to work with your groups on your input modeling report, which is due, I think, at the end of the week. So the input modeling report is kind of like a lab report for the lab, but there's no formal lab there. So details on that input modeling report you can find online. There are some sample input modeling reports. I think I grabbed like 4 or 5 ones I thought were pretty good from a previous semester, and I put those online. This is a group submission. It allows us to take a look through what you're planning to do and give you some feedback. The ideal situation is for you to actually go out and say, these are the inputs that I'm going to sample, and actually go out and sample a few of them and fit some input models on them. That's what we would traditionally do. If that puts your group at a point where you feel uncomfortable taking data on the real world system, then you can find some surrogate. That surrogate could be, you can go to some of these webcam repositories out there. So for example, you can find a webcam that just looks at a coffee shop in New York City, for example. So if you were to Google for some of these, like WorldCam, I think is one of these sites, then you can use those as places to observe. It's not as great as being in the thing that you're looking at, but for like a traffic intersection or something like that, it's not so terrible. Alternatively, I've kind of already put you through the ringer with the previous lab on a bunch of different types of data sets and fitting them to models. And so just for this semester, I would be okay with saying, well, as long as you identify what input models you need, and then go out and find some sort of way to parameterize them that is intelligent. So, you might Google for some stats on a particular, you might have to take some guesses, but as long as they're justifiable, then we may not actually have to have you fit, specific models like you did in Lab 8. So ideally, you reproduce Lab 8 for a data set that you've gone out and found, and you've actually started taking some data on that. But if worse comes to worse because of the COVID situation, I'm also fine for you just identifying those inputs that you need to model, and then start modeling them with auxiliary information that you can justify, again, with sources and things like that. You should also identify what outputs you're going to take from your system. If you're going to compare your simulated system to the real world to see how well they match, for example, or if you want to, or what outputs you're going to look at in your simulated system to tell that you had a performance improvement. So those outputs, you need those as well. So all these details are listed online in the input modeling document, and the desired format. This is not meant to be a long document. It's like 1 to 2 pages. So it's mainly just supposed to be showing me that you've put some thought into the project, so that over the next month, you can actually do the whole project. All right. Other assignments, there's some Canvas activities, not that many left over. So there's one more that's due before lecture J1. So this is lecture H, then there's lecture I on Thursday, and then J1 is next week. Then there's only 2 more Canvas activities. And then there's a final review Canvas activity, similar to how we had before the midterm. So, but these are the last 2 Canvas activities that have new content on them. Homework G3 has been out there since it's been formally announced last week, but it's been out there for longer than that. It's got 2 questions, just like the previous homeworks. The first one is on input modeling. So you'll be doing a chi-square test on data that are ostensibly Poisson. And then the second one is on output validation. And so we'll talk about that this lecture, but you'll end up doing a power analysis on a t-test on a paired t-test. And that's kind of what you're doing there. Both of these are covered in the book as well. So if you're working ahead, then those resources are already out there. And then there's only one more homework left, and that is an arena-based assignment based on the inventory modeling assignment that we've done before in the lab, and that's homework J2. It is already out there in case you want to start on that. Questions. So I know last time there was a question about the lab report grading, and the TA had some health issues that put him behind. I've also recruited now some additional help from the instructional assistant to grade some of those lab reports. And I noticed just this morning that some of those numbers are starting to come down. So we should hopefully get you those reports back real soon, or you'll at least start seeing a lot more progress on that. All right, so any other questions that I can handle?
I have a question.
Yep.
So on the project, my group is trying to come up with how we're going to collect our data. And we wanted to know if there was like a minimum or recommended amount of data points that would be good to find a distribution for.
Well, that's kind of a question that relates to a lot of the topic from today, which is about statistical power. It kind of depends on the variance in your system, and I'm going to try to make that more quantifiable in today's lecture. But the basic gist of it is, if you're taking a lot of data and you find that you've got that there's not a whole lot of variation from sample to sample to sample, then you probably can get away with not that much data. If you find there's a huge amount of variation, then in order to characterize that variation, you need a lot more data. So one thing you can do before you go out and gather a whole bunch more data is ask, are there obvious reasons why I'm seeing such huge variation in my data? For example, if you were modeling a bank and you were doing inter-arrival times, if you took inter-arrival times, at 9 a.m. one day and at 4 p.m. another day and at 2 p.m. another day, and you pooled all of that data together, you're going to see a huge amount of variation in those inter-arrival times. But that's really because there's probably a different arrival rate at those 3 different times. If you just focused on 9 a.m. or just focused on 2 p.m., then you might find that you're going to get less variation and you can get away with sampling a lot less. And what I mean by get away with sampling a lot less is it's like the parameter estimates you get for the model, the input model, like the exponential, will converge pretty quickly with only 20 data points. If you gathered 200 data points, you wouldn't get a very different parameter estimate. And so I'll try to put a finer point on that as we move forward. But I would say that the general idea is, if you're seeing lots of variation, ask yourself, how consistent are my sampling conditions? Am I managing to introduce variation that I haven't modeled, like from time of day? And can I get rid of some of that variation? And then if you really feel like you have designed a good sampling strategy, then you have to say, if I've got lots of variation to the point where my confidence intervals on my parameter estimates are gigantic, then I just got to take more data. And so you'll gradually compress those down. For the input modeling report, I think it's okay to just view this as a pilot study. And so you can say, well, we went out and we took 20 samples or something like that. And then you can characterize kind of the variation in that, and then tell me if you think you need to gather 100 samples, or if you think that the variation you saw was pretty light, and you're done with your sampling for that. Does that help?
Oh yeah, thank you.
Mm-hmm. Any other questions? Great. All right. So let's roll on forward. So let's start with an attendance question, just to get everybody warmed up. So the question, this comes from last lecture, and so I've actually got it all on the slide here. So it's pre-prepared. So if you looked at these slides ahead of time, you knew this was coming. And so I want you to sort of choose one or more of these letters for your attendance response. And then once you're done putting that in there, I would like to sort of see a poll of this. And so go ahead and put your answer, and these could be multiple letters, in the chat, but don't hit enter until I tell you. And then when you hit enter, then we'll see what people respond to. So I'll mention the chat. We've got an attendance question, and I'll put the link as usual. And then the question is on the slide. And so choose your answer or answers, plural and put them in the attendance question response as well as in the chat, but do not hit enter. So I'll just read this out loud. I should be most suspicious of blank p-values when I have blank number of samples, where the first blank is either low or high, and the second blank is either small or large. So we're thinking, what are the conditions that you should be most suspicious of? And so go ahead and think about that. We talked about this a little bit last time. And go ahead and again, put your answer in the chat and go ahead and hit enter so that we can see an idea of roughly where people have put their answers. All right, I'm seeing a lot of D's. I'm seeing a couple of C's and a couple of B's, no A's. So if we think about it, so let's handle, since I see so many D's, let's take a look at that case. And so high p-values, we'd say that under the null hypothesis, then these data are kind of highly likely. That's what a high p-value means. And so if I have high p-values, but I have a small number of samples, then yeah, I would agree that I would be suspicious of this D case down here. So maybe I'll turn on my annotation. And so I kind of agree that D seems like should be pretty suspicious of that, because high p-values mean that, you know, it could have happened under the null. But if you have a very small amount of data, then, you know, if you only flip a coin once and it comes up heads, well, it had to come up something. Any hypothesis about the coin's distribution could be supported by that one. So yeah, small data is definitely something you should be, if you have small data, small number of samples, you should be very suspicious of high p-values. So then it makes me wonder, are there conditions where you should be suspicious of low p-values? And so, you know, if we look at low p-values, we mentioned here and mentioned here. And I see a lot of answers here for C. And so that suggests that maybe this is the one that we should be suspicious of. And I also would say that that's the right answer there too. So as a review there, if you get low p-values, you know, I think in 380 and maybe 385, you might be taught that, like, I don't know, somehow it's a success if you found a low p-value. A p-value less than 0.05 is somehow good because you've detected a difference. But the thing is, if you have really, really, really large data, then you will detect a difference eventually. Like, you just gather more and more data. There is an effect of whether or not you believe Pluto is a planet or not. It has gravity, and that gravity may be having an effect on my mood. We could build a statistical model for my mood that has Pluto in it or does not have Pluto in it. If you took enough data about my mood, eventually what you'd find is that Pluto has an effect. You would detect that effect, and then you more importantly detect that my data would differ from a model that didn't include Pluto's effect in it. But it's such a small effect that the fact that I got a significant difference, statistically speaking, is not realistically practical. So large amounts of data should make you skeptical and worrisome about low p-values, very low p-values. And your next question should be, what is the effect size? And that's something we're going to get into today, is this idea of effect size. So keep that in mind. All right, are there questions about that? Is it making sense to people why the high p-values, you should then look and see how much data they had. And if they have not a lot of data, don't trust it. And if they're low p-values, you should look at how much data. And if they have large amounts of data, you should ask, what is the effect? How big is the effect? So any questions? Okay. All right, let's clear that. All right, so let's do one more one. So the question here, so again, I'll put the link in the chat to make it more accessible. And oh, that was a direct message to an individual. I apologize for that. So the attendance question, link. And so now the second attendance question for today is a test with higher statistical blank will reject a false hypothesis with fewer samples. And so go ahead and put that into, again, let's just do for kicks, let's do it both into your attendance response as well as in the chat, but don't hit enter. So the enter key is lava for a bit here. And so, and then fill in what you think the right answer for that is here. So here I'm just trying to teach you a term that should become very, very commonplace as you move forward in your statistical career. So we talked about this term last time very briefly, but I want to see if you remember it. If you don't, that's fine. These are just graded for coherence. Put whatever you think is actually right in there. So, okay, so take your answer and both in the attendance question and or both in the attendance form as well as in the chat. In the chat, go ahead and hit enter and let's see a survey of what people say. Right, so far I'm seeing a lot of powerful answers, a lot of answers with the word power in them. And that's the answer that I was looking for here, is the answer was power. So a test with high statistical power means that it will reject a false hypothesis with fewer samples. Well, what does that mean? What that means is then if I have a test with high power and it does not reject my hypothesis, I can have more confidence that the hypothesis is actually true. So if you want to get anywhere close to accepting a hypothesis, so this is good for goodness of fit. If you say, I think these data are from this input model, in that case, you might look for a test that has a high, that gives you a higher p-value so you don't reject the hypothesis. But you can only really trust it if it has high statistical power. And so the higher the statistical power, then the more trustworthy it is, even at lower numbers of samples. And we will talk about today how you can actually measure power. So yeah, are there questions about that? Does people get that? that's the term looking for power. And we're gonna then talk a lot more about power today. So if that isn't very familiar to you yet, it should hopefully become more familiar today. Okay. All right, so again, more lingo things here. The term positive, it means that we have detected a difference from a null hypothesis. So you hear people talk about true positives and false positives. The term positive means a detection. So this is the most conventional way of doing things. You say, I think things are this way. And if I detect that the data are not that way, then that is a positive result. So, so that's what we mean by positive, is that you assert a null and you detect a difference from the null. That's a positive result. It sounds like it could be a negative result because I'm in some ways rejecting a null. That sounds like a negative thing. And then sometimes people might use that term that way, but the more conventional way to use the term positive in statistical speak is detecting a difference. It's a detection of a difference from what you might have expected from the null. So we use the level of significance, otherwise known as alpha or type 1 error. This is the probability of rejecting a true hypothesis. Written in probability speak, given that the hypothesis you've asserted is true, what's the probability that you are going to just reject it by chance? So you have a hypothesis test, a t-test, a chi-squared test, or whatever. You can then measure the type 1 error. And you do that by giving it data that actually are from the true hypothesis and see how frequently your test rejects those data as not being from that hypothesis. And so if you set, if a test has alpha equal to 0, which like in a t-test, a chi-squared test or whatever, you can set the alpha by setting the threshold levels for discrimination. If you set your threshold level so that the alpha is equal to 0, then you end up not rejecting any hypotheses. And the good thing about that is then you've got no false rejections. So you have no false detections. But the downside of that is you don't detect anything. So it's kind of a degenerate case. Similarly, if you set your alpha equal to 1 by adjusting your threshold so that alpha is equal to 1, then you detect everything as a difference from the null. So all of the hypotheses are rejected. So it's so again, low critical values, again, not very useful. But that kind of gives you an idea of how, as you slide from 0 to 1 in your alpha, how it changes the rate of these false positives. And then, we've got this p-value, which greatly relates. So whereas alpha is kind of a threshold p-value, then the p-value is the actual probability of the observed deviation, again, if we assume the hypothesis is true. And so this is all I'm saying down here, is that alpha is our threshold for p. And so this, just like we've got critical values in our test statistic, if we turn our test statistics into p-values, then each one of those critical values of the test statistic corresponds to an alpha value that will be a critical value for the p-value. So you can convert a test statistic into a p-value, and you can convert a critical value into an alpha. And so all that should be kind of review. What might, which hopefully this is still review, but is starting to get a little bit new, I hope, is that there's also beta, which is our type 2 error rate. Beta is the probability of not rejecting a false hypothesis. So in a universe where the asserted hypothesis is false, so you say these data, I know you said these data were uniformly distributed, but I am going to say that, well, let's say they're actually not uniformly distributed. Well, if they weren't uniformly distributed, then what's the probability that I would still say that they were uniformly distributed? So we view this as a false negative, because we built a test that was supposed to detect deviations from uniformity, and we gave it data that were not drawn from a uniform distribution, but it failed to detect the deviation. So that is a false negative. So it was a negative because it didn't detect a deviation, but it should have, and that's what's making it a false negative. So saying that in the book, they, the null hypothesis, whereas I'm saying the null hypothesis is false, in the book, they might say the alternative hypothesis is true. So these are just equivalent ways of saying the same thing. All right, so this power term that we just asked you about, this is just 1 minus beta. So this statistical power actually means something. And so it's not just a weasel word, or it's just not just a general term. Statistical power actually means 1 minus beta, or the probability that your null hypothesis is rejected, given that you're in a universe where your null hypothesis is actually false. So that's what we mean by statistical power, is that the hypothesis is false and you reject it. So it is a so-called true positive rate. And so if you have a test that has a high statistical power, then what you're saying is that it is a high true positive rate. So that's the reason why when we want goodness of fit tests, like the chi-squared test, the Komogorov-Smirnov test, these tests we use to test how good a fit is. So when we see high p-values coming out of them, we want to know, can we trust those? Well, saying that they have high statistical power means that they have a higher than normal true positive rate. They're optimized for their true positive rate, which means we can trust them more when they don't reject. So when we can actually view them as kind of like accepting our chosen hypothesis. So you throw a uniform distribution into a chi-squared test and it comes up and the p-value is not less than 0.05. Whereas in other tests, we might just say, well, we failed to reject the uniform. In the chi-squared, we actually can try to go a little farther and say, we actually have confidence that these data are uniform because this test has so much statistical power. So in order for us to figure out how much power a test has, then we have to do what's called a power analysis. And we're going to do a basic power analysis in this lecture, if we get to it, and also on your homework in homework G3. And a power analysis is a tool that is used to determine how many samples you need, and that goes back to the question that came from earlier today about the project, and or how small of a difference can be detected given a sample size. So I can detect differences smaller and smaller and smaller given I've got more and more data. So then what this will say is for this particular test, for these variants that you see in your data, for these number of samples, this is the smallest effect that you can actually detect from the null, the smallest difference from the null. Alternatively, you can go to the power analysis in the first bullet and you can say, all right, I need to be able to detect differences that are this big. So I've got my null hypothesis and it's a normal distribution with an average of 5. If things are 5.5 or higher, I need to be able to detect that. So I need to detect a difference of 0.5. I don't care about differences less than 0.5, but if it's 0.5 or higher, I need this test to be able to detect that. And so what a power analysis will do is you can put in the variance of your data and you can put in that 0.5 and it will tell you how many samples you're going to need to be able to confidently say that you have enough power to detect the difference, so that if you don't detect the difference, then most likely the difference is less than the small difference threshold that you put in. So that's the purpose of a so-called power analysis. And again, we'll do an example as we move forward. All right, and so the way these things relate together, the false positive rate and the true positive rate, is usually drawn on one of these things called a receiver operating characteristic, or ROC curve. So this is something that if you take a machine learning class, you'll probably get introduced to these. For whatever reason, the traditional statistics curriculum doesn't often introduce these things. Partly it has to do with culture. I kind of come from both worlds. And so to me, I think in terms of these things. And so, so basically every statistical test that you have, you can plot, you take a bunch of data, you do a bunch of tests where you test that statistical test on data that you know came from a hypothesis or didn't come from that hypothesis. And you can calculate the false positive rate and the true positive rate for that test. And for different alpha values that you put into that test, so different critical values, you can sweep over those different alpha values. And for each one, you do a bunch of different statistical tests and you say, what is the average true positive rate that I got for the set false positive rate that I put in? And you'll end up getting a curve that looks like this kind of hump-shaped one. So the diagonal curve here is just if you replace your test with random chance. So if you just drew a random number between 0 and 1, and you asked, is that number less than my false positive rate? You would end up getting this diagonal line right here. And so your statistical tests hopefully lift you off of that diagonal line because they hopefully do better than just flipping a coin. But and if they're really good, then you hopefully they go up very high here. So if I were to go and annotate, like a really good statistical test is probably, I'm trying to find my annotation tool. Where did it go? Okay, so a really good statistical test would be very peaky here, would go up very high, and it would look something like that. But real statistical tests aren't that good. They're usually somewhere in between down here, like these 3 statistical tests that happen to be shown here. And what I want you to see here is there is a fundamental trade-off between type 1 error and statistical power, which is effectively between type 1 error and type 2 error. So if you ask for a low type 1 error rate, you will necessarily ask for low statistical power. Likewise, if you ask for high statistical power, you are necessarily going to ask for a higher type 1 error rate. So these tests that have high statistical power, what you're going to end up finding with them is although you can trust them when they don't reject a hypothesis, you can't necessarily trust them when they do reject a hypothesis. And hopefully you saw that in lab 8 with the Komogorov-Smirnov test, is if you have lots and lots of data with a KS test, it tends to be overly conservative and it rejects more often than maybe it should. Okay, so we'll see this curve in the next couple of lectures as well. So with that, are there questions about these basic terms that are kind of brought up that we're going to be using more and more as we move on in the class? Statistical power, false positive rate, true positive rate, false negative rate, true negative rate, etc. Any questions? So the question was, alpha and beta are inversely proportional. That's a great question. If statistical power here, you can think of beta as being like the flip of that, because it's the 1 minus. And you do then sort of see this thing that, well, if I were to draw, there's going to be this kind of relationship here, where if I have an alpha equal to 0, then I'm going to have a beta. So this is my beta curve. That will end up being higher. And I think that should hopefully make sense, because basically think about that. If your alpha is equal to 0, you're not rejecting anything. Well, if you're not rejecting anything, then you're accepting everything. So that means you're never going to sort of, your beta kind of ends up getting fixed up here at 1, because you're just kind of defaulting to allowing everything. You assume everything is the true hypothesis. The other way around is if your beta goes all the way down to 0, then you're down here. Then that means that you kind of never accept anything. Well, how do you never accept anything? Well, you always reject. And that's what alpha equal 1 is always reject. So yes, you can view there is a fundamental trade-off between alpha and beta. The shape of that, I don't want to say they're inversely proportional, because it's not a line. It can be like here, you can see with statistical power, it's a bit of a curve. And so the goal when we design statistical tests or machine learning algorithms, our goal is to try to bend away from inverse, from the linear relationship. But overall, the trend is still going to be this trend that's kind of drawn here, or if you view in statistical power, the dotted line that's drawn here. But our goal is to bend it away from that, because if you're just on the dotted line, you're basically doing random chance. Any other questions? Okay. Great. All right, I'm going to skip that attendance question. So I'm pretty sure that, so I don't want to spend a lot of time doing too much review here, because I want to make sure I cover the things that we didn't cover. But I just, again, want to highlight that when you calculate variance from a sample data set, make sure to divide by n-1 if you're using the sample mean in your variance calculation. That n-1 is really important to get unbiased estimates of variance. And so last time we talked about, again, taking these summary statistics and how to take those. We then also jumped ahead and talked about maximum likelihood estimation. So we were saying that for things like the Poisson distribution, that parameter alpha, which goes into which isn't level significance, just the Poisson parameter, I can estimate that by either taking a sample mean or a sample variance. They both should be equal to alpha. But in the same data set, mean and variance, the sample mean and sample variance are not going to be equal to each other. So which one do I use? How do I choose the best formula to estimate these parameters? And when you know the probability mass function, or when you know the probability density function for a distribution, you can use a little calculus, and then that will end up allowing you to do this, what's called the maximum likelihood approach, or maximum likelihood estimation. And so we demonstrated that with, turn off my annotations here. So we demonstrated that with the exponential, where we said that if I've got a bunch of interarrival times, I can, if I take all those interarrival times and I put them into a probability density function for an exponential, and I solve for the rate, which would be sort of most likely if I saw those data, then I end up getting this formula out, where the maximum likelihood rate for an exponential is just 1 over the average times that I got out of that interarrival process. And so that's a nice convenient formula, and it actually makes a lot of sense. And there are a bunch more of those. And so the book lists several of them, and I've grabbed 4 of them here. And like I was saying with Poisson, even though you could estimate this Poisson parameter by taking a sample variance, if we do this mathematical game with the Poisson distribution's probability mass function, then what we find is the maximum likelihood estimator is actually the sample mean, not the sample variance. So even though both technically from the distribution, the actual mean and actual variance should be equal to this alpha, the sample mean and sample variance are always going to be different, because they're samples. And so there's going to be confidence intervals around them. So my best bet is to use the sample mean, not the sample variance, to estimate this parameter. And so we've got a bunch of those. And so a lot of them, fortunately take formats that make sense. For a normal, it makes sense that the best bet for choosing the mean of a normal is the mean of the sample data set. The best chance of choosing the variance for a normal is the variance of the sample data set, so long as you use that unbiased form that divides by n-1 instead of divide by n. And I think by default, if you calculate variance in, say, Microsoft Excel, I think it uses the unbiased form by default, and you have to toss it a flag to go to actually do the biased form. So that was maximum likelihood estimation. So any questions about those before I cover our modifications to the chi-squared test and KS tests that you'll use in part 1 of your homework? Okay. All right, so in your homework, you are going to be analyzing count data that is supposedly from a Poisson distribution. And so you'd like to test it against the Poisson distribution. Whenever I give you count data, you should think, so from my childhood, I had Sesame Street and there was this, this count. And so, Sesame Street is still in the culture. So hopefully this reference makes sense here. But the idea here is that whenever you hear the word count, the statistical test you should think of is chi-squared. Chi-squared is a test of counts. Do I have the expected number of counts given the counts that I have taken here? So I have an expected count of observations versus an actual count of observations. And so what you're going to do with the chi-squared test is we've already used the chi-squared test or test for normality. Now we can generalize it to test for any distribution that we want. And so what we end up doing here, and this is just a summary, and I'll show an example here in a second, but whereas before in the uniform case, the expected number of counts to be in each bin would be the number of data divided by the number of bins. Now we generalize that and we say, okay, what is my bin? And so it might be, any number from 1 to 2. Any number from 1 to 5.5, whatever your bin width is, or your bin size is, you can calculate what is the probability that I would get an outcome in that bin. So you can use an integral, for example, or a sum to calculate that probability. That probability, which will be between 0 and 1, because it's a probability, you then multiply that by your number of samples, and that will be the expected number of counts in that bin. Otherwise, it pretty much runs almost identical to the same chi-squared test you did for uniformity. You, after you decide on your bins, where your bins are from the range of your random variable, you take the expected number in each bin, and you take the observed number in each bin, and you calculate a chi-squared statistic. Again, like you've hopefully seen in 380. And then from there, from this chi-squared statistic, you can then look at the table and then decide whether we've rejected the hypothetical distribution or not. One of the tricks that we need to keep in mind, though, is that you only can use this test if the expected number of counts is greater or equal to 5. And I will talk more in detail about where this 5 comes from in lecture I. But for now, just know that you need them to be greater than or equal to 5. If you have a bin that has less than 5 counts in it, you have to choose a bin next to it to combine them with. So you get a larger bin that will hopefully then have at least 5 expected counts in it. Not observed counts. I don't care how many observed counts are in the bin, but the expected counts, that has to be 5 or more. And then the only other thing to look out for, and this is a slight deviation from before the midterm, is that the degrees of freedom. Before the midterm, it was just the number of bins minus 1. Now that we're after the midterm, the distributions that you're testing may include parameters that you estimate from data. Remember, like when you're calculating sample variance, you estimate the mean and you put that into the formula. That's an estimated parameter. If you estimate the Poisson distribution and you're not sure what mean to use, and so you just estimate the mean from data, then that needs to be accounted for in the chi-squared test, the same way it needs to be accounted for in the sample variance calculation. And so that's why we subtract from the degrees of freedom in the chi-squared test by however many parameters you've estimated. If you've only estimated the mean, you put a 1 here in the S parameter here. If you've estimated mean and variance, you put a 2 down here. If I give you the parameters and they say, test whether these data are a Poisson with mean 5. In that case, I've given you it. It hasn't been estimated from data, so there are no estimated parameters. But if I have not given you a parameter, if I've asked you to estimate the parameter from data, you have to count up how many parameters you've estimated and reduce the degrees of freedom in the chi-squared test by that. Okay. So let's try to make that a little, and this is for those who are interested in the math behind it. I've got kind of a slide on degrees of freedom, but we're already kind of running behind, so I'm not going to go into that too much. But these are kind of other examples of what I've mentioned here as examples of when you estimate parameters and when you don't. And so if they're, like I said, if they're normally distributed and I get the mean and data both from if I get the estimated mean and estimated standard deviation, both from the data set, they weren't given to me ahead of time, then my degrees of freedom are my number of bins -1, as usual, -2, where this 2 correspond 1 to the mean and 1 to the standard deviation. So my degrees of freedom for the chi-squared test are n -3, as opposed to the n -1 that you would have used before the midterm. But instead, if I told you specifically you were estimating, you were trying to fit or evaluate the fit of a normal with mean of 5 and variance of 2, in that case, I've given you those parameters. They were not estimated from data. And so I just go back to the standard n -1 is my degrees of freedom. Now, there are a couple of cases like the uniform distribution. Its parameters do not decrease the degrees of freedom. And so it's only those parameters that you have an arithmetic formula that ends up calculating them. So like in the case of a mean, I know that a mean is data plus data plus data plus data divided by total number of data equals the mean. That puts them on what's operations researchers call a simplex. And so if there's an arithmetic formula that links your data directly to a parameter where there is no way to move that parameter without moving a piece of that data, then it restricts the degrees of freedom, which is why you have to subtract 1. But in the case of a uniform distribution, the A and the B that go into the uniform distribution, it's true you might take them from the range that you look at in your data set, but if you moved a point in the middle of your data set around, it's not going to change these A's and B's. And so the outside boundaries of a uniform distribution or a triangular distribution, they do not count as reducing your degrees of freedom. And you'll get a feel for what we mean by this as you work with this more and more. And I won't throw any, these are special cases I'm mentioning for you for your career, but on a test or whatever, it'll be very clear when you need to reduce the degrees of freedom in a test and not, like on a midterm or a final exam. All right, so we've done this goodness of fit test before, the chi-squared test before. This is actually the same example that we did before the midterm. And so I'm not going to spend a lot of time on it because it's pretty much exactly the same. I will highlight that after I give you all of these data and you cut them up into bins, you calculate the expected number that you'd find in each bin, and you have to make sure it's at least 5. And then you go to your table and you take the number of bins -1 minus any of the estimated parameters. There were no estimated parameters for this uniform case. Look up that critical value, and then there you go. So that's exactly what we did for a uniform distribution. And then how do you calculate the expected counts for an arbitrary distribution? I already mentioned this, but basically you're going to take the probability that an outcome would fall inside that bin, and you're going to multiply that by the number of counts. And so for your homework G3, you're going to be basically using this formula, because in your homework G3, you're going to be testing a hypothetical discrete distribution. And so in that case, you're going to choose bins, which will probably be your outcomes. And if you've got an outcome that has an expected count in less than 5, then you're going to have to combine it with outcomes next to it. and you combine it with outcomes X. So now instead of being your bin being just outcome 1, it might be outcome 1 and outcome 2 together. So now your bin is 1 or 2. And so you can then add up the probability from outcome 1 plus the probability for outcome 2. And that gives you your probability of that larger bin. If you multiply that by your total number of samples, that tells you the expected number of samples in that larger bin. And that's the example that you'll be doing on that homework in that first problem. Okay. And so I'm just going to skip through this for time, but are there general questions on the modifications for the chi-squared test?
Hey, Professor, quick question.
Mm-hmm.
In your normal distribution example, so let's just say you had 4 bins and you found that between 0.5 and 0.75 there were less than 5. Now, do you combine it with the 0.25 to 0.5 or the 0.75 to 1? How do you combine that bin? And then do you effectively have 3 bins now?
Yeah, excellent question. Thank you for asking that. Your goal, every time you combine, you lose a bin. And your goal is you want the highest degrees of freedom possible while still maintaining the requirements for the test. So in your particular case, if I've got a bin that is got less than 5, what I want to do is want to look for the bins next to it that I can combine with that reduce the number of combinations I have to do. So if there's a bin next to it that's also less than 5, but I combine those two together and the combined bin will be greater than 5, I do that one combination and I'm done. What I don't want to do is take this one that's less than 5, combine it with a bin that was already greater than 5, and then take the other one that's less than 5, combine it with a bin that's already greater than 5. Now I've lost, 2 bins. So I want to keep as many bins as possible, because if you remember from when we introduced the chi-squared test, or just even thinking about histograms, the coarser you make the bins, the harder it is for you to discriminate from the uniform distribution, because eventually you just get moving towards having like one big bin, and one big bin is not very informative at all. Does that make sense?
Yes.
Great. Any other questions about this chi-squared test?
So just to be clear, you would not collapse a bin if it alone was less than 5, but the ones around it were 5 or more. Is that what you're saying there, if I understood correctly?
Well, if you have to, if your only choice is to collapse, you have to get rid of the bins that are less than 5. You have to. And so it may be that there's only one bin less than 5. In that case, just pull it into one of the other bins, and it's kind of arbitrary which one you choose. I might choose the one that's smaller, just because it kind of needs the most help in getting over it gives you that kind of better margins, but it's not going to matter too much which one you pull it into. But I'd say maybe as a heuristic, just pull it into the one that's closest to it that's as the smaller count. All right. Okay, so one question that I'm hoping comes up to some of you is that, well, what do I do when it's impossible for me to have bins that are this full? That what happens when my only option is to have the only way I can get bins that have 5 or more is to have like 1 or 2 bins, and that ends up like not being able to discriminate among any distributions. Well, that's why we have tests that have higher statistical power than the chi-squared tests. And one example of that we've already seen is, so this is, what happens when this is the case. I have so little data, basically the number of samples is so little that this is impractical for my case. In that case, I go to the Komogorov-Smirnov test. And so the KS test is all about sorting. That's why there's a sorting hat on the screen. And so the nice thing about this sorting approach is I don't need to coarsen things. I don't need to bin things up. That's what gives it higher statistical power, but it's also going to make it super, super sensitive when you give it lots of data. So if I gave the KS test a huge amount of data, it's probably going to find a difference, even though there's no real difference between my data set and my hypothesized distribution. There might be a small difference, but it's a difference that I really would rather it not notice. It's practically insignificant. So exactly in the cases where the KS test is bad is when the chi-squared test is good. Exactly in the cases where the chi-squared test is bad, the KS test is good. So they're complementary tools. So how do we modify the KS test for the general case? And so in general, the KS test is a way to measure the distance between empirical CDFs and reference CDFs, or the difference between two empirical CDFs. And so if I have two data sets and I want to test whether they came from the same distribution, I can use a KS test for that as well. So it's particularly useful when sample sizes are small, when no parameters have been estimated. You can use it in some special cases when parameters have been estimated, but in general, if parameters have been estimated, it's not a good test to use. And it is just generally more powerful than the chi-squared. The good thing about that is you can use it with little data. The bad thing about that is it doesn't perform well with large data. So how does the KS test work? Maybe I'll just skip ahead to the example that you've seen before. So this was the example from before the midterm. So I gave you 5 data points that might be uniformly distributed. And what you did is then you asked, do they fit into the right interval? So if I sort them, then this red number and the green number that's kind of sandwiching the sorted data point, that's kind of the interval that I would expect it to fall into if it was uniformly distributed. And then you measured the differences between that and the boundary, and you kind of took the biggest difference. And the biggest difference was your decision parameter. And so when we want to generalize this, what we do is we take the data and we run the data through the CDF for the hypothesized distribution. So I've got data points here, and let's say I want to test to see whether those data points are exponential. Well, what I'm going to do is I'm going to take my hypothetically exponentially distributed data, and each data point, I'm going to put it into the CDF. That will turn every data point into a number between 0 and 1. If I've picked the right CDF, then the transformed data will be uniformly distributed. And that means that the KS test is basically a test for uniformity on the transformed data. So that's how you apply the KS test, is you send your data through the CDF for your hypothetical distribution. And then that gives you numbers between 0 and 1. Sort those numbers just like you would pre-midterm, and then see if those fit into the right intervals. And then measure the maximum distance there. And then that distance you can go and look at the standard table in the back of your book. So what I want to point out is if you get lots and lots of data, the critical values get really, really, really small. So basically what that means is that the KS test can discriminate between very, very, very small differences between a hypothetical distribution and your actual distribution. So if you, for example, get a parameter slightly wrong, if you have enough data, the KS test is going to find that and it's going to say wrong. But that's probably too sensitive. And so the KS test tends to be overly sensitive in those cases, which is why you probably want to use a chi-squared test when you have lots and lots of data, because again, these thresholds get really, really small as you get lots and lots of data. All right. So, so sort of a summary there of the chi-squared test or the KS test pitfalls. Not really good with estimated parameters except for a couple of special cases, and super, super sensitive for high amounts of data. And I'm hoping some of you are familiar with that, because after Lab 8, you ended up running these input analyzers, and you got both the chi-squared test, the chi-squared test and the KS test outputs out. And in some of yours, what you may have noticed is that the chi-squared test would not reject a hypothesis, but the KS test would. And so here, it might be hard for you to read the numbers, but the if I were to zoom in on this, then we can see for this data, which to me looks like it's triangular distributed, like it really looks like it's a triangle. It's almost like we're just doing the tests as a formality. Sorry, I can't resize in that direction, so I have to resize in the wrong direction and then expand. So as you can see down here, hopefully that's readable, that for these data here, for this triangular distribution, the chi-squared test says it does not detect a difference, but the KS test, the test statistic is super, super small, which basically means it has not seen much of a difference from the expected CDF. And yet it still has a p-value that's less than 0.05. So the KS test rejects the triangular. And that's probably not because the triangular was a bad choice. It's probably because we have so much data down here, 5,000 data points, that the KS test is just way too sensitive. So it's more like, whereas the chi-squared test is saying, yeah, this looks pretty triangular. The KS test says, no, you picked the wrong triangle. And, but if you look at it, this isn't the wrong triangle. This is a perfectly reasonable, like the distribution I picked is totally fine. So that's why you just have to be careful. You can't just blindly go by the p-values. You have to think about the context of how much data you have and how much statistical power your test has. All right. So that's the stuff that I meant to make sure we covered in G3. Are there any questions about that? All right, great. Okay, so, and I'll just mention there are some other tests that are even more powerful than the KS test that you'll see in statistical tools like the Anderson-Darling test. Again, these are so powerful that they're really meant to be goodness of fit tests. They're not really meant to detect differences from a hypothesis. They're really meant to be for if you've got small amounts of data. You need to build up confidence in whether these small amounts of data could have plausibly come from a certain distribution. And that's what these kind of tests are for here, the Anderson-Darling test. And then one that you'll use a lot if you start doing t-tests and ANOVAs and things like that is the Shapiro-Wilk test, which is not only a high power test, but it's a high power test designed exclusively for normality. So if you want to test normality and you have very little data, use a Shapiro-Wilk. And so I'm not going to go into how Shapiro-Wilk works, but by the end of the semester, you'll have Shapiro-Wilk burned into your head as like the test you would run before a t-test, because you can't run a t-test unless they're normally distributed. So high power tests that are meant to use for low amounts of data to confirm a fit. Okay. And then always, it's never a bad idea to throw in a probability plot. So a QQ plot is always a great thing to couple. If you're trying to convince a stakeholder you've picked a right model, the p-values only go so far. Ultimately, something visual is much more convincing. So a nice QQ plot showing a nice linear fit to your data and your hypothesis ends up, being, it speaks volumes. All right, so maybe skip these things and let's maybe, all right, so I am going to try to move through some of this stuff relatively quickly so that we make sure to get to things that are most relevant to the bottom half of homework G3. So far we've done input modeling, and now we're moving into the section of the course where we're focusing more on the outputs. And so what I've got here is, the testing whether we had the right input models. That is important. But then after we've taken those input models and put them into our structural models from ARENA, we then need to look at the outputs and then need to see, do our outputs actually match the real world situation? So given that our inputs match the real world, do our outputs match the real world? And if our outputs don't match the real world, even though the inputs match the real world, then there's something wrong with our model that we need to fix. So there are three terms that we're going to be using here, throwing around. Verification is basically debugging. Verification is, did I code it up correctly? I wanted an exponential distribution. Did I actually get an exponential distribution out? So I take a histogram of generated numbers from my sim and verify that they're really exponential. If they're not, then apparently I didn't implement an exponential in my sim. And then there's validation, which is generally, is the structure of my internal model correct? So I put the right inputs in, do I get the right outputs, the right shaped outputs? If my outputs look totally different in sim than they do in real life, then maybe I need to fix these things here. Now the process of fixing, and that might mean putting new blocks in, or that might mean just altering parameters, is what we refer to as calibration. And so that's improving the caliber of a model is calibration. And so this feedback process of constantly iterating back through is our process of making the models more and more realistic. So validation tests how well we're fitting, calibration tries to make them fit better. So those are the three terms that we're going to be throwing around from here on out. And so this is the basic process. Sometimes it's shortened to be referred to as V&V or TV&V, testing, verification, and validation. And then there's also kind of calibration. And so you've got your conceptual validation and your model verification. So model verification, again, is the debugging. So did I actually code what I wanted to code? But then there's the validation step of, did what I want to code actually match what is happening in the real world? That's the big difference between validation and verification. And this is just sort of summarizing that. But as I leave that up there, are there questions about that? Are these three terms clear to you? Verification, validation, and calibration. And I'm not going to read through all this. It's kind of, this is just kind of a summary of these terms. All right. So let's work through this example here. So we've got a validation of a bank drive-through model. So I've built a simulation of a bank drive-through, and it has these 4 lanes, for example, and I'm interested in knowing how long does it take for a car to enter the bank drive-through and get its stuff done and then leave the drive-through. So I built a little model. And so my model looks a little bit like this. The model is here. I had to come up with my random variables. So this is like your input modeling report. This is the things that you're deciding. Like all the things on the left here are the things that I want you to put in your input modeling report. Which random variables are you going to need to model as inputs? What are the decision variables that you need to put, that you're going to put into the system to experiment with? So I say, well, my arrivals, they're Poisson counting process arrivals. My service times, maybe they're normally distributed. My decision variables, I'm going to only have one teller. And then this you wouldn't maybe think of as a decision variable, but the mean service time, that sort of is like a training parameter. You can say to a manager, at what point do you stop kind of whipping people, you know, to the point where their service times are fast enough? At what point do you stop training people when their service times are fast enough? And so here we're saying that we're assuming that you can get the human service times down to 1.1 minutes. And then, you know, a single line. So we've got a single teller and a single line. So those are our decision variables. Now on our outputs, we can measure how busy the teller is, the teller's utilization, what fraction of time the teller is actually doing work. We can measure the average delay of each of the customers coming through there, and we can see how big the queues are, so the maximum line length over time. So like I was saying, that's kind of the domain of input modeling. And then, but we're sort of focusing now on these outputs. So the output validation here. So you go out, you gather data from these things, and you collect a response. So you collect those outputs, and as I've mentioned before, you want to make sure you collect them all from the same time period, because the arrival rates might change over different time periods. So you only collect them from, say, 4 p.m. or something like that. And then I'm going to take my outputs. And so I know that the simulation, so I know that the real world outputs are an average. So I said Y2, if I go back, that's the average delay. I can say in the real world, I know the average delay is 4.3 minutes. So what I want to do is I want to generate a bunch of different simulation runs and see what the average delay is coming out of my simulation runs and see if they're significantly different from 4.3. So my null hypothesis is that the average coming out of my sim will equal the average from the real world. In other words, will equal 4.3. And so I run a certain number of replications. I might need to run more replications for reasons that we'll see moving forward. And then for each replication, the verification step is I can actually see, did I generate exponentially generated inter-arrival times? Did I generate normally distributed service times? And I can do verification. As long as they come up and they both look exponential and normal, then I can move forward to the validation. And then the validation step is actually seeing what is the delay that comes out of my simulation at the very end, and how does it compare to 4.3? So I get a data set that looks like these. It looks like these data right here. These here, the Y4 and the Y5, that's for my verification step. And let's say I've gone through and I've said, yep, this actually was exactly the type of inputs that I wanted, and same with this one. Then the question is this third column. Does this third column have a 4.3 minute average time? And so how am I going to test that? Well, this is where we introduce the t-test again that you should remember from 380. So it's specifically referred to as the one sample t-test. And so our null hypothesis is that the estimated variance or the null hypothesis, the two populations, the real population and the simulated population, have the same mean delay. That's our null hypothesis right here. And so we are going to take an average of the simulated delay times. That is our so-called one sample. That's why it's a one sample t-test. And we are going to compare it against the hypothetical value from the real world, from 4.3. And so the idea here is that if all of our data are independently drawn, so we have independent simulation runs, and all of those independent simulation runs are independent of the real world, then we can, and all of our data are from a normal distribution. So that's why I might need to check normality with a Shapiro-Wilks test, as we'll talk more about in future lectures. Then I can use a t-test. And my t-test will tell me is whether or not a 4.3 average is consistent with the data that I gathered. And so I end up doing that. I end up taking the sample standard deviation, the sample average. I generate a t-statistic that comes up to have a magnitude of 5.34. I look in the back of the book and I see that for an alpha value of 0.05, a level of significance of 0.05, and 6 samples, then the critical t-value is 2.5, which is much smaller than 5.34. So that tells me that there is something wrong with my simulation, that I have built a bad simulation. I need to go back into the simulation and see what I've not accounted for. And so I go back in and I find out that the thing that I didn't account for is that the tellers working the windows are also working the inside of the store. And those tellers working the inside of the store, they are going to slow down the tellers working the windows. And so I need to account for the additional service that is happening inside the building. So I go and I do that. I maybe build a additional in-store walk-in model in order to properly, to properly deal with the additional delay that would be generated from inside the store. I gather new data over here. And then now I've done my new t-test. And then I find out that now it's fine. This output delay here is got a small t-statistic, which means that I cannot reject the hypothesis that these have a 4.3 minute average time. The problem is I don't know if I can actually accept the hypothesis that these have a 4.3 minute average time. So all we can do now is, without verifying that we have enough statistical power, is just say that we're not rejecting the 4.3. We now need to go back in and calculate our statistical power. So that is what we're about to do. Are there any questions so far? This is hopefully just a review of how to use a t-test. I've given you a hypothetical average, and I've given you some data, and you average those data, generate a t-statistic based on the difference of those two, compare that to a table. And if the number is too large, then most likely your data were not generated with that average. If the number is small, you can't really say anything until you've done the next calculation, which is statistical power. All right, and we're probably going to have to pick this up next time, but we are finally getting very close to catching up with the delay that I generated a couple of lectures back. And so actually maybe rather than rushing through that, I can tell you that if you're working on the second part of homework G3, the next couple of slides will be very helpful, especially the slides that are down here about these operating characteristic curves. All this is covered in the book as well. I will start in the next lecture on this, but I just feel like if I keep going right now, I am going to end up just rushing through it, and it's not going to be useful for either one of us. So why don't we instead just hop in a little early, and we'll just end on an attendance question. And then I'd be happy to take questions about the material today other than that. So the attendance link, put in the chat. And so the attendance question that I'd like to ask here is there are three terms: verification, validation, and calibration. Which one of these terms is associated with making sure your conceptual model of the system matches the real world system? So of those three terms, verification, validation, and calibration, which of those three terms corresponds to just testing that your conceptual model of the system, what's in your head, matches what's going on in the real world? And other than that, that's all I'm going to put you through today. And so happy to take questions if anybody's got them. If you don't, then I will see you Thursday.
Hey, Professor.
Mm-hmm.
So just to confirm, after we have finished after this lecture, we're able to do everything that we need in the homework?
Well, so this lecture's content is all the content you need for the homework. So I will go over this at the beginning of the next lecture as well, but all of the stuff that you need for the homework is also in the book, because it's basically just a modified textbook exercise. So you can also find it in the book, but if you're just looking for like, where do I need to stop? Like all this stuff about statistical power and the paired t-test. So if you flip back through this lecture, example 10.3 in the book, for example, that does this paired t-test, that will be very useful. And then the other example that'll be useful for the book is this, I thought I actually had a numerical version, but there was an earlier example in the book which involves this power analysis. And I think I refer to it on the homework, and it shows you how to use this operating characteristic curve.
Okay, thank you so much.
Mm-hmm.
Hey, Professor, so do we have the input modeling report due this Sunday, basically? I don't know if you discussed it already.
That's right. That's right. It's basically the lab report for this week, because there's no lab this week.
So we should have an idea of our project data collected and run it through input analyzer?
No, well, you should have a 1 to 2 page description of what you want your project to be, a list of what you think important input variables are, a list of what you think the decision variables are, and conceivably some pilot data for 1 or 2 of those input variables to show me that you've gone out and sat with the system and gotten some idea of what will be necessary to take data. It's true that you might have 10 input variables. I'm not asking you to gather all the data for your project. I'm just asking you to kind of demonstrate that you have access or ability to estimate some of the parameters that you'll need for some of your input models. And there are example input modeling reports online. Again, just 1 to 2 pages, basically proposing what you're going to do.
Okay. So the general strategy for the input analyzer is we look at the mean square first, and then we might look at the chi-squared, and then we look at the ks. And you're saying there might be a trade-off between the chi-squared and the ks depending on, I guess, the sample size, and maybe that the fact that they trade off with one another. Is that kind of a general strategy we should be looking at our data with?
Yeah, I mean, so that's, you have to view the input analyzer as a dumb tool. It basically runs a bunch of tests at once that may be useful to the designer. It is not meant to be making the decisions for you. And so when you look at the R-squared numbers that it sorts everything by, usually the top couple of models are the good ones that you should be thinking of. And then from those, you can then say, okay, well then let's make sure that one of these wasn't rejected by a chi-squared test. Because it's rejected by a chi-squared test, that's probably a bad sign. But I guess what I'm saying is that if it is rejected by a KS test, that's not necessarily a bad sign. So I guess what I'd say is if you see that it's been not rejected by the KS test, then you probably have, and there's a lot of data. Like if there's a decent amount of data and it's not rejected by a KS test, you've got an excellent model. So you kind of learn over time how to balance these things to come up with a good argument for why you picked one model over another. The last thing I want is for you guys to prepare your presentations at the end of the semester and you to show me an input, or even in your input modeling report, you to show me an input model. And from that input model, you say, this is definitely exponentially distributed. And the histogram doesn't even look quite right. And the chi-squared test shows that it's got a p-value of 0.0001. And just so you can have these awkward times where, because people didn't think through the test results, they'll take the R-squared as the be-all end-all. It may just be that you need to go out and gather more data, or maybe even though it had a best fit, it was actually a poor fit. So view the input analyzer as a starting point, and then try to use all of the knowledge you've built up over 380, 385 in this class to make a better pick of your own, and then just justify that to me.
Okay. Also on part 3 of lab 8, I tried to model the inner arrival times as Poisson, but it was grayed out in the input analyzer. Like it didn't let me select it. I'm wondering if there's like, but the distribution after that, for whatever reason, it let me select it. So I don't know if
right, well, so remember that a Poisson is only for discrete data. It is count data. Okay. And so inter-arrival times, durations, this gets a little confusing because we refer to a Poisson process, but a Poisson process is, has associated with it exponential inter-arrival times. And so those inter-arrival times are probably better fit by an exponential. Now, if you instead counted how many occurred, then those would be a discrete count, which would allow, and what the input analyzer tries to do is it tries to only give you the Poisson option if it has detected discrete data.
Okay, I see. So if it found like decimal points or something, maybe in the data.
That's right.
All right.
But if it just found counts and they were all positive, then it would do the Poisson.
Okay. And lastly, I was just wondering, I was surprised that with the randomly generated data, and then you take the difference between each subsequent data point, it ended up being an exponential. Did you discuss why that ends up happening, or is that in one of the lectures by chance? I just found that surprising.
Yeah, that's a little more advanced, and I wasn't meant to, and I basically wanted to, that as you take more classes in probability and statistics, you'll learn why that's the case. And I was mainly meant to be a teaser for some of that. And it was a way in which I could get you to generate data that were exponentially distributed that were maybe in an unexpected way. But basically, if you, I mean, you've learned about Poisson processes, hopefully not only in this class, but also in 470. And if you uniformly distribute points on a line, let's say a number line from 0 minutes to 10 minutes, if you uniformly distribute points on that line, then then basically what you've done is you generated a Poisson process. So like I've I kind of told you how to generate a Poisson process where you start with the exponential. So if everybody arrives to the bank and they're exponentially weighted into arrival times, then there are going to be spaces in between them. So if you look at the time of series of when they arrived, then you end up getting points from 0 to however long the interval was. Now, if you stand back and look at where all those points are, it turns out they will be uniformly distributed across that time interval. And so you can actually flip it the other way. For any time interval, if you uniformly distribute points, what you'll have done is generated a Poisson counting process. And so in that time interval, the uniformly distributed points, the differences between them will be consistent with the Poisson process. In other words, they'll be exponentially weighted. So it's kind of a, you can go either from so another way to view it is if you take an exponential distribution and you sum them all up, then that summing will, if you kind of stack them on top of each other, then and then look at the interval that you generate by stacking them all on top of each other, then all of the breaks in between them as they're stacked on top of each other will be uniformly distributed. So they kind of relate to each other. If you take a class on measure theory or on probability, then you'll learn about maximum entropy distributions. And it just so happens that the maximum entropy distribution for an interval is a uniform, and the maximum entropy distribution for the space in between points that are in an interval is an exponential. And so that's another reason why they kind of fit together. So it's a little bit more of an advanced topic. I'm glad you noticed it. It was meant to kind of be a teaser, but it's sort of outside the normal scope of this class. So you won't be tested on that, but keep it in the back of your mind because it might come up in other classes later. Any other questions?
Is there a possibility that you would post solutions for Lab 8? Because I guessed on a lot of the distributions just based on the numbers, but I couldn't really provide a good justification, if you know what I mean.
Well, Lab 8 was supposed to be a bit subjective. And so I don't want to give you solutions for Lab 8, well, for two reasons. For operational reasons I have to do with the class, but also because I want you to see that all models are wrong, but some are useful. And so the kind of the focus of Lab 8 was to get you to that uncomfortable point where you put out a model that you're asserting are a substitute for these data, recognizing that your model will not be perfect, but did you generate a model that captures enough of the data to be useful? And that's kind of the practice there. So even if I gave you answers, I don't want to say that my answers are the right answers, but my answers might, I might make different choices than you, but that doesn't mean that your answer is a wrong answer, as I guess is what I'm saying there.
Okay.
All right. Well, with that, I think people are going to start coming in for my next class. So I'm going to end the meeting. And if you did come in for my next class, just rejoin, and I'll see everybody else on Thursday.